And I want to take some time today to talk to you about Chapter 1, Forces, which is maintaining equilibrium or changing motion. So now that we've talked kind of about all of the internal forces that the body has with the skeletal system, muscular system, and then how we control those forces with the nervous system, we're going to actually get down to the nitty-gritty and start learning some of the math concepts involved with measuring performance. First, starting with forces. So what is a force? A force by definition is a push or a pull exerted by one object on another object. Forces, as you'll learn a little bit later, always come in pairs, and they're going to be equal in size but opposite in the direction that each force is applied. So for example, if I take my hand and I push into my hand, the force of going one direction of pushing into my hand is going to be equal to the force of my other hand pushing back. If they are in equilibrium, these forces are paired and equal but opposite. The causes, or what tends to cause, the responsibility or response of these forces is to cause acceleration. So acceleration can be in a positive direction or a negative direction. If an acceleration is in a positive direction, things are speeding up. If forces and acceleration are in a negative direction, they tend to slow down. This means that any force can cause an acceleration, either positive or negative, and this can cause objects to start, stop, speed up, slow down, or completely change direction. The English unit for force is a pound, but for the purposes of this class, we're going to use newtons. Basically, this is 1 kilogram of force times 1 meter per second squared, which is our acceleration unit. So most of the time what you're going to hear is force in the frame of newtons. So characteristics of force. First, all forces are going to have a magnitude. So this is the size of the push or the pull force that is occurring. Next, it is going to have a direction. So this is the line of action in which this force occurs. There's also going to be sense. So this is the way where force is pushing or pulling. And then there's going to be a point of application. So this is where the force is actually coming in contact with whichever object is being used. So if we're sitting here and I have my pen and I'm going to push it along a table, how forceful I push this pen is going to determine how far it goes. So that's the magnitude. Direction, if I push the pen in the line of the pen and it slides this way, that is a line of action with the pen. If I push down, this would cause the pen to stay in place. I'm just applying force and it's not going anywhere. Sense, so way force is pushing or pulling, and the point of application would be where my finger contacts it to push along the table. All right, so for example, we could sit here and we can look at this shot putter, and we could figure out a couple different places where force is occurring. So for example, the red arrows here, you have the force of the shot put acting on the shot putter, and then the force that the shot putter is putting into the shot put. These are going to be equal and opposite. We can also talk about a few other types of forces. So for example, the force that he is putting into the ground and then the ground is putting back up into him. We could talk about the force that's occurring at the other arm, which is going to cause a rotational motion because the forces are imbalanced. Lots of different things to consider, but in the simplest form, you would just talk about the shot put on the shot putter and the shot putter onto the shot put. Say that 5 times fast. All right. Another important thing we need to note is force is a vector quantity. So what is a vector? Basically, this is how we define things with magnitude and direction. So we talk about the differences between, say, speed and velocity. So speed, I just know how fast somebody is going. So like your speed limit is 65 miles per hour. However, if I wanted to turn this into the vector quantity, which is velocity, I would still say 65 miles per hour, but now I'd say they are traveling north. So speed 65 miles per hour, vector quantity, velocity 65 miles per hour north. All right, so vector gives us a lot of information. Force we tend to represent graphically with an arrow because this gives us magnitude and direction. So the length of the arrow is the magnitude of the force. The arrowhead indicates the force sense or direction. The shaft of the arrow indicates the line of application, and one end of the arrow indicates the point where the application is being applied to the object. So we will do some free body diagrams in a little bit when I do the math demo. So just know that arrows matter in biomechanics. All right, so where we're going to kind of start, we're going to do something called rigid body mechanics. Basically, we're going to assume everything is rigid. There's no flex, there's no air friction causing problems, there's no give in things. Everything's a rigid body, and everything's going to kind of work as a point of mass or a particle. So even though I could have my pen, we just assume that it is rigid. Well, it is rigid, that's nice. And then all of its mass is in one point. We know that's not true, but when we're doing the math, that's what we're going to assume is true. All right, we're going to also assume all forces on the body have the exact same point of application at the center of mass, and the effect of these forces acting on the body are not going to be impacted by any dimensions or changes. So we're just assuming everything's going to work in a perfect math state. We know that's not accurate, but we're going to make the assumption anyways. All right, so next we need to talk about how we classify force. So we've just spent a lot of time talking about internal forces. These are forces that act within an object or a system, so that muscular contraction, skeletal compression, all of this. It's going to impact the object, but it does not affect the motion of that object. So muscular contraction is a force that is internal, but I'm not necessarily changing the shape of the object. So basically these forces are meant to hold things together. So tensile force, compressive force, just kind of all of those forces that we've been talking about so far. What is going to be new is external force. So these are something that's going to act on the object or the system from the environment. So we have three main forces here. We have contact force, so when objects touch each other, non-contact force, the objects are not touching each other, and then gravitational force, which is the weight of the object. All right, so these are all going to impact our external. So here's what is special about non-contact forces. These forces are going to be paired, but they're still not touching each other. The best example we have here is weight, which is a kind of subclassification between a non-contact and a gravitational force. All right, so weight is the force of gravity acting on an object. Very simple formula here. Weight equals mass times the acceleration due to gravity. So weight is a force, so it'll be in newtons. Mass, we tend to convert to kilograms because this is a science class. And then the acceleration due to gravity is 9.81 meters per second squared downward. So that is a vector. All right. Typically, we just say 9.81 meters per second squared. We'll talk about how direction matters here in a little bit. But sometimes when you're doing quick math in your head, as scientists, we just round things to 10. So pay attention in your questions on whether it's asking for an exact answer or an estimated answer. So if we're asking for an estimate, just round to 10 so you can move quickly through the problem. If it's asking for an exact number, you're going to want to use the 9.81 meters per second squared. All right, so here we have a basketball player. Basically, this individual, once they are in the air, they can't really change their motion. All right, if you think about it, the force has been applied. There are now no longer things interacting with each other. The only thing that can interact with this player is gravity. All right, unless this individual slams into them, then we have another force interaction. But basically, once you are in motion, once you have left the ground, the only thing you can do is respond to gravity. So you're not doing anything really that you can change your motion once it's begun. All right, looking at our contact forces, these are when two objects are going to touch each other. They're going to act separately on this object. We call this a reaction force. So contact forces can be resolved into their components. So a normal contact force tends to be perpendicular to the two objects in contact. So basically I have a pen, and then if I were to contact it, I'd run perpendicular and it would go straight up. So if I were to hit the pen, just go straight up. All right. If you have any sort of parallel contact force, this is a friction force. So if I were to take this pen and try to slide it across that imaginary desk that I have again, what's going to end up happening is no matter how much force I applied, eventually the force of friction of the table is going to slow this down to a stop. All right. This is opposing motion. So we deal with friction all the time when we participate in sport. This can be a good thing or this can be a bad thing. So for example, think about basketball shoes. All right. They make that lovely / horrible squeaking noise because they interact with the floor. All right. If you think about basketball shoes and if you have, like, say, a dusty floor or shoes that haven't been cleaned very well, you're going to not stick to the floor when you need to change direction and you're just going to keep sliding. That's very dangerous. You're going to get hurt. That would be a point where we want friction. Now, if you think about something, say, a hockey player, which glides along the ice, and their puck glides along the ice, that would be a point where we really don't want a lot of friction because we want to move quickly. We can also see this in, say, machinery. So when we're talking about ball bearings in mechanical components, they're trying to reduce the friction as much as possible to make the machine move efficiently and effectively. All right, so here we have an individual running. We have the runner's foot. It's going to contact the ground. You're going to have a friction force of the shoe gripping the ground so it can pull the individual forward. And then you have the force of the individual's weight impacting the ground and then going right back up into the individual. So a couple different forces at play here. All right, so let's take a little bit of time to talk about friction. So friction is very important for sports performance, and that is because it opposes any sliding in between the object and whatever it is in contact with. This means we're going to have an interaction between surface molecules. We have two different types of friction. We have static friction and dynamic friction. Static friction, this is when the two surfaces are not moving, and then so they stick together. So for example, we have maximum friction here with the pen. I can't untwist it anymore. Molecules are locked together. All right, this is going to hit a limiting point. I can apply enough force to overcome static friction. If I overcome static friction, this means this object is going to slide. All right, dynamic friction is when we have two surfaces that move past each other. This is known as sliding friction or kinetic friction. So if I were to try to untwist the pen the other way, once I overcome static friction, I can take the pen apart. That is sliding friction. Friction didn't go away, it just changed its state. It's no longer static, it is now dynamic. We also know that friction is going to be proportional to the force pushing these two surfaces together. We tend to refer to this as R. So the greater R is, the greater the friction is. All right, and again, there are moments where we want friction to be high and moments when we want friction to be low. Also, the characteristics of the materials that are interacting is going to really matter when it comes to talking about friction. So for example, my car tires on a road, all right? If you think about car tires on a road, they have treads. They're trying to grab the road. The thicker your treads and the appropriate characteristics for your road are going to allow the tires to grip the road and you maintain contact with the vehicle, or sorry, maintain control of the vehicle and contact with the road. However, let's say it starts to rain. Now I have lowered that constant of static friction, and I have now made it harder for those tires to grip the road. And if you overcome that static friction, you're going to start to slide. And this is known as hydroplaning. You don't want to do that. All right, so the characteristics of your material, if those are going to change at any point, this is also going to impact friction. All right, so the friction equation is friction times mu, which is the coefficient of friction, times R, which is the contact force. Whenever you solve problems with this, pay attention to how the problem is worded. Is it asking for the static coefficient of friction, or is it asking for the dynamic coefficient of friction? So a good example here, if I am asking you what force would be required to slide a box, all right, and I know the mass of the box, but I'm trying to figure out what it's going to take to get it to slide. That means I have to have a force greater than static friction. It'd be really easy to plug in the coefficient for static friction plus whatever this contact force is, typically it's weight, and figure out, hey, if it is, let's say 1300 newtons, I need anything greater than 1300 newtons to start sliding the box. If I say, what is the coefficient of friction on a already sliding box, now I'm going to use the kinetic coefficient of friction. So just pay attention to how problems are worded. All right, when we take forces, we can also add them together. Because nothing is in wonderful, beautiful perpendicular lines. So the net force is the sum of all of the external forces acting on one object. This is your resultant force. And we're not simply summing up all of the external force magnitudes because direction matters. Remember, these are vectors. So I can sit here and say, what is the effect of 200 Newton objects on the 200 Newton forces on a particular object? Well, if I have 100 Newtons going this way and 100 Newtons going this way, and they can connect to each other, they're canceling each other out. Nothing's moving. Now, if I have 100 Newtons of force here and 100 Newtons of force here, it's going to make a triangle, and it's going to kind of go off in a direction. All right, if I have 100 Newtons of force and then another 100 Newtons of force, I can't twist, but yeah, we're going that way. We're going the same direction now. Then it's going to be 200 Newtons of force, and it's all going to go in one direction. Direction plus force matters. So pay attention to those together. All right, another thing we want to talk about is collinear forces. So this is when we have one or more external forces with the same line of action. One typically is positive and one is typically negative. So one's going this way, one's going this way. Now, if we want them to be perfectly matched, you're going to have static. If one is greater than the other, the object will move in that direction. You just subtract them from each other. So if I have 100 Newtons this way and 70 Newtons going this way, which direction is it going to go? 170. It's going to go with the 100, and it would be 30 Newtons of force that way. You just subtract them. All right, so let's talk about some barbells. Here's our example here. So consider we have a spotter helping lift a, You have a spotter helping a lifter with a barbell. They identify up as the positive direction and down as the negative direction. The barbell weight is 1,000 newtons, that is acting downwards, so negative 100. The lifter is pushing up with 980 newtons of force, so this lifter ain't going to make the lift. And then the spotter is also going to help them pull up with 90 newtons of force. So our net force, so figuring out whether this lifter is going to make the lift or not, is going to be the lifter plus the spotter plus the weight. So we have the lifter pushing up with 980 newtons of force. Then the spotter pushing up, that should say 90 newtons of force. And then you have the weight pushing down 1,000 newtons. When you add that all together, you have a positive 60 newtons of force moving upwards. That means this bar is going to clear. All right, hopefully that example makes sense. All right, we can also have concurrent forces. These are forces that are not collinear, but are going to act through the same point. All right, so we have a gymnast hanging from a grab bar. The coach applies force to the front and the back to stop a swing. So we have 20 newtons of force posterior directed from the push to the front, 30 newtons anterior pushed from the back, and 550 newtons of force of the gymnast on the gymnast's hands from hanging. All right. So what we have going on here is we're still working at the center of mass, but we have somebody who is hanging, and they're going back and forth like this. They're swinging. So if I apply the right amount of force, I can prevent the back swing, the front swing, and I can make somebody static. All right. These are not going in the direction of the force of gravity going up and down. All right. They are going side to side. If you get excessive forces that are concurrent forces, what's going to happen is instead of linear movement, you're going to get rotational movement. Right? So this is going to be really important when you get into more complex movement patterns. But basically, I can add forces anywhere at the center of mass, and it's going to cause different characteristics of movement. So, sounds like a good test question. Collinear forces are linear, hence collinear, and concurrent forces or concurrent forces can cause rotation. All right, So to calculate this, all we'd have to do, we'd solve the net vertical force, solve the net horizontal force, and then we would do the Pythagorean theorem. Do we remember the Pythagorean theorem? A squared plus b squared equals c squared. And then we would just figure out the resultant force angle. So if you're applying enough force front to back, I get static. If I don't apply enough force front to back, we're going to get a swing, start of that rotation. All right, so still talking about our gymnast, the horizontal forces, that posterior push was -20, our anterior push was +30. We also had our vertical forces, so they were holding onto the bar with a +500 newtons of force, and then their weight was pulling down with a -500 newtons of force. So we figured out the weight because the gymnast was 50 kilograms, and we just did a quick estimate of 10 meters per second squared for the acceleration due to gravity. All right, so we got some resultant forces going on here. So before you go on, take a minute. These horizontal forces, are they going to move anterior or posterior? Vertical forces, are they going to move up or down? Ponder. Have it? Move on. All right, so -20 plus +30 means we have a +10 newtons of force. This means this individual is going to move 10 newtons to the right. Then they're pulling up with 550. Their weight is only 500, which means they are going to go upward 50 newtons of force. So this person is going to go up and slightly to the right. All right. So knowing this motion, I can actually use Pythagorean theorem, and I can figure out how many newtons of force is actually going on. So resultant force, if you remember, a squared plus b squared equals c squared. So that is the equation up here. You plug in your 10 and your 50 from your horizontal and your vertical, run some math, square root of 2600 means 51 newtons of resultant force is how much actual force is being applied to this individual. All right, I hope you feel okay with that. Kind of hate I'm not in class to have a whiteboard to figure this one out with you, but hopefully this makes sense the way I'm doing it. All right, so now that we have found the resultant force, now we need to figure out the angle of the force. So hopefully we all remember a little bit of trigonometry and the lovely concept that is SOHCAHTOA. So if we remember right triangles, we can figure out degrees and lengths based off of SOHCAHTOA. So S-O-H, that is sine, stands for opposite over hypotenuse. Cosine, which is adjacent over hypotenuse. And then TOA, which is the tangent, which is opposite over adjacent. So if we look at our right triangle, we do not know the hypotenuse angle, but we do know the forces involved in the adjacent and the opposite angle. So in this case, we would use tangent. Since I don't know the angles, instead of using tangent, I would use arctangent. So here we can see theta, which is what we use for degrees, is the arctangent of 50 over 10, so TOA, opposite over adjacent. And this would give us the arctangent of 5, which when you put that in a graphing calculator that is set to degrees, you get 78.7. So we know that this gymnast is going to move at a magnitude of 51 newtons at an angle of 78.7 degrees. So they're going to take off at a slightly upwards and outwards angle. All right. So then sometimes we have external forces that are not collinear, and they're not acting in just strictly horizontal and vertical directions. So for example, coming back to our shot putter, you have about 100 newtons of force at 60 degrees, so coming out here from the shot putter's hand, and then the mass of a shot put is 4K, so it is a women's shot put. How would we figure out the resultant force here? All right, well, we would just make our triangles. So we know we have 100 newtons going outwards, and then we know that we have a horizontal component, and then from here, we have our horizontal force going out, and then we know it is at a 60-degree angle. Since we know an angle, and we can make a right triangle, using SOHCAHTOA again, we can figure out that the horizontal component is 50 newtons, and the vertical component is 87 newtons. So I will send you guys a YouTube link if you guys are kind of need the refresher on right triangle math. I'll send you a YouTube link after I have sent out this video. So just if you're a little lost right now, it's okay. I will give you a resource. All right. So again, if you like the math, horizontal component, vertical component, we're going to use cosine here because we know the hypotenuse and we know it's coming at a 60-degree angle, so that would be the bottom of our right triangle. We don't know the adjacent side. We just kind of go through, do sine of 60 is going to give us our components. So hopefully this makes sense. All right. Also, because we now know the horizontal and the vertical forces, from there we can figure out how far the shot put would be thrown. So if we know the shot putter's force is 50% horizontal, that's really awesome. Don't need to figure out anything from there. However, we said the vertical force was going to be 86.6. Well, if we know that the shot put is 4 kilograms times 10 meters per second, and it's going to be finding us negative 40 newtons, and we know that the vertical force is going in the other direction, that means truly the only vertical force we're working with is 46.6 newtons. So even though the shot putter is applying 86.6 newtons of force, the shot put is going to fight them negative 40 newtons, which means our true force is only going to be 46.6 newtons. So that is just the resolution of forces. So even though the shot putter is applying the 100 newtons of force at a 60-degree angle, we're truly only going to see 50 newtons horizontally and 46.6 newtons vertically. All right, so Pythagorean theorem. Now that we know what this is going to look like, you just do your a squared plus b squared equals c squared. We've seen this already. This will give us 68.4 newtons is what is actually being seen, even though they are applying 100. So we are losing due to gravity and some other things here. So let's figure out the release angle. He's applying it, or she. This is a female shot put weight, so we're going to go for she. My apologies. Female empowerment on the shot putters. We know the horizontal force is 50. We know our calculated resultant force is 46.6. Same thing with the arctangent like we've done previously. We figured out that it is at 43 degrees for the release angle. So we started with 60 degrees of 100 newtons of force being applied by the musculature. And what we ended up with was moving this 4 kilogram shot put 68.4 newtons at an angle of 43 degrees. We lost a lot of force in here, and it's just basically how it was applied. Also, that would be a pretty good throw, just saying. All right, so the last two concepts, I've given you some math problems to work through. I want to talk about static equilibrium. So this is when the body is not accelerating or is no change in motion. Static equilibrium does not necessarily mean stillness. It just means that we're not accelerating or decelerating. So this is going to be constant velocity or actual stillness. All right, so if we have a skater that is motionless on the ice, that is 50 kilograms, you can use a free body diagram to visualize the situation. And basically, we love to come back to static equilibrium to figure out where our external forces are coming from. All right, so we have our skater. She's doing a really great job of just sitting still. All right, you have the force of her body weight pushing down into the ice, and then you have the ice's reaction pushing back up into her. Nothing is happening because the forces are equal and opposite. All right, so if we wanted to just do this analysis, we know that the skater is 50 kilograms, 50 times 10 is negative 500 newtons. That's weight going down. We know she's static, so equal but opposite. That means 500 newtons have to go upwards right back into her. So that is the end of this kind of starting discussion on forces. Basically what I need you to know, I need you to feel comfortable manipulating Pythagorean theorem and comfortable with your triangles. I want you to understand that forces tend to be equal and opposite, and forces can be internal or external, and depending on how they are applied, either collinearly, concurrently, or some variation thereof, it's going to impact what we actually see in the real world. So I hope this is helpful. I really look forward to seeing you guys in class on Tuesday. And have a lovely weekend. Bye, guys.